my group members and I will be presenting on our ASAS 1 Assignment 2 presentation. I am Valarie and my group members are Jin Guan and Ryan. So I'll give you an introduction to composite materials. Composite materials are a mix of two or more different materials together. The individual material properties and identities are remain and mixture has superior properties. It is tailor-made to satisfy a set of requirements, and in conclusion, it is actually a composite materials consists of a combination of materials mixed together to achieve specific structural properties. What are the advantages of composite? It is lightweight compared to metals. It has a typical lower thermal expansion coefficient. It has the ability to have a complex shape as one piece as it reduces assemblies. It is typically more corrosion resistant except for carbon plies with aluminium, and is more fatigue resistant than metals. The main components of composites are resin, which is the matrix, and fibres, which is used as reinforcement. Resin and fibres do not dissolve or merge completely. The properties of composite materials are typically superior of that of the individual materials. Fibres are laid in layers using a resin system, which is a matrix, and therefore composites manufactured this way are known as laminates. So in laminates, the main components are there's fibres and resin. Fibres is the primary load-carrying element of the composite material. It is strong and stiff in the direction of the fibres, which is usually only in one direction, and is designed so that the fibre orientation produces optimum mechanical properties. It can be designed so that the fibre orientation produces mechanical properties, but it is only approached to the true isotropic nature of metals. Next, I'll be moving on to the matrix. The matrix supports the fibres and bonds them together in the composite material. It transfers any applied loads to the fibres and keep the fibres in position and selected orientation. It provides environmental resistance to the composite structure and determine the service temperature of the composite structure. Fibre orientation. The strength depends on the orientation of the fibre to a large extent. So different strength materials have different axes of fibre orientation inherent to the material. There are many ways fibre can be oriented. For example, if it's unidirectional, the fibres only run in one direction. So strength and stiffness are only in that one direction, which the fibre is laid out at. Or it can be bidirectional, which fibres run in two directions, typically 90 degrees apart. So there is strength in both directions, but the strength might not be the same. It can be quasi-isotropic, which is stacked in 45 degrees interval. It simulates the properties of an isotropic material, such as aluminium or titanium. Or it can be a rub clock. The positive angles can be measured in clockwise or counterclockwise direction. A rub is actually a longitudinal fibers of the fabric. So it shows the high strength direction due to the straightness of the fibre, and is used to describe the direction of the fibres on the diagram. Many composites have symmetrical and balanced layup, as it reduces the internal stress and avoid distortion during the curing process. Symmetry is very important, as for each layer above the mid-plane of the laminate, there must be an identical layer below the mid-plane. The identical layer must be of the same thickness, same material properties, and same angular orientation. And balance is achieved by having every layer centered at a positive angle, and an identical layer must be of a negative angle so that it balances out.
So these are the types of the composite materials that are used in aircraft applications. So why is there a recent push in the composite materials in the aircraft industry history? Well, as you can see from the graph here, the weight percentage of aluminium decreases over the years from 1960 to 2020. From 80%, it has went down all the way to 30%. This is because there are new composites added into the industry, and this is why aluminum is starting to decrease in the aircraft. So among these years, the materials added were fiberglass composites, carbon fiber composites, metal matrix composites, reinforced carbon-carbon radar absorbing materials, and among this decade there's a new material added to aircrafts which is called glare, which I will be talking about later. And as you can see from the graph on top, the weight percentage of composites increased from 1960s to 2020s. So manufacturers are looking for ways to make planes that can improve the performance of the planes, reduce weight, which overall boosts the fuel efficiency of the aircraft. Manufacturers also want to make sure that the passengers are more comfortable in the planes and they have a high strength to weight ratio when they are using composite materials. So these are the common types of composite materials that are used in the aircraft. From this picture, we can see that carbon laminate composites are mostly used in the aircraft industry, and they make up about 80% of the composites used in the aircraft. There are other composites which are also used, and there are also there are very little aluminum and titanium materials used in the aircraft. This is because after the year 2000 they have introduced a lot of composite materials to the aircraft. So the common types of materials that planes use are fiberglass, aramid, which is also known as Kevlar, and carbon fiber reinforced plastics, CFRP. Fiberglass is a composite material which is made of glass fibers and epoxy resin. It was first used in aircraft by Boeing in the 1950s, and in the airplane itself, it is mainly used in chairs, wings, and aircraft domes, which are at the front part of the aircraft. Its advantages are that it's lightweight, it's chemical resistant, so when the plane is in the sky, there won't be much corrosion happening. It is good at transferring heat around, which has good thermal conductivity, and it has a very good ability to mold into complex shapes, such as the domes and chairs, where the shape has a lot of curves and edges. Next, we have aramid, also known as Kevlar. It is a yellow-colored organic fiber that is 43% lighter and twice the strength as fiberglass. Its properties is that it is high strength, it has good impact resistance, and it is weak in compression, which makes it difficult to cut. It is used in mostly, as you can see in the picture, the aircraft fan casing and aircraft engines. We also have carbon fiber reinforced plastics, also known as CFRP. They are mostly used on composites and aircrafts, and they have a very good corrosion resistance. They have also a high strength to weight ratio, which makes it very light and can withstand a lot of strength when the aircraft is undergone a lot of structural loads. Its applications is that it is part of the fuselage, wings, and empennage, which is basically almost the entire aircraft. Hence, carbon fiber reinforced plastics are the most common type of composite used in the aircraft today. There are recent developments in new cutting-edge composite materials, such as the carbon nanotube technology. This nanotube technology is an arrangement of atom sheet layers of carbon, better known as carbon nanotubes. It is one of the strongest materials available for the application in aerospace industry today, and it can be used to replace carbon fiber composites. There are also ceramic matrix composites, also known as CMC. The CMCs have excellent properties of thermal resistance and with improved techniques of manufacturing, and it overcomes many shortcomings of the monolithic ceramics that are somewhat used in today's airplanes. They have high toughness and they are generally used in regions of high temperatures, such as turbines, combustion chambers, and airfoils, as seen in the picture. We also have another development, which is metal matrix composites, also known as MMC. They have oxide nitride or carbide reinforcements which are embedded within the matrix. The matrix is made out of aluminum, or can be used as aluminum or titanium. They are rather more flexible and have higher fatigue life. Hence, they are often used as rotor blades or the fan blade or turbines. The most common development that has been researched today is the glass laminate aluminum reinforced epoxy, also known as GLARE. GLARE is a fiber metal laminate composite of thin metal layers of aluminum which are bonded together using an epoxy matrix. Its main advantages over conventional aluminum is that it has better damage tolerance, especially in impact and metal fatigue. It has very good corrosion resistance, which is slightly more than the normal carbon fiber composites, and it is easy to fabricate, making it low in specific weight.
Composite materials in aircraft applications. So what are the types of possible damages on composite materials? Firstly, we have manufacturing damage, which includes fiber breakage, matrix imperfections, delamination and debonds or disbonds, and the combinations of damages. Next is the in-service damage, which includes liquid ingression, erosion, corrosion, and UV radiation. Next, we'll be talking about damages on composite materials compared to traditional materials. Under loading, the metallic material will generally have a crack that initiates from a specific point and then propagates and leads to failure. This will be the traditional type of material, while now I'll be talking about the composite type, which the damage in composite materials is completely different. It is where a large number of microscopic events will develop very gradually over a large volume of material. Types of damage assessment or inspections. There are three types of repairs. First is the permanent repair, which restores strength and properties of the original structure such as stiffness and durability. It satisfies original part damage tolerance requirements. And lastly, restores functionality of aircraft systems. Next is the interim repair. Interim repair is where temporary repairs are less demanding, and if the repair needs a certain duration, permanent repairs are preferred. Interim repairs may damage parent structure. And lastly, we will talk about cosmetic repair. Cosmetic repair does not affect structural integrity. It is carried out to protect and decorate the surface. Next, I'll be talking about what are the challenges faced by manufacturers and maintenance organizations in terms of repair practices and equipment required for repair. It will be the over-reliance on past experiences, such as their previous job or previous methods that they have done, and the difficulty of detecting damages, the insufficient experience and training, the controlling of costs, and the equipment, whereas improper operation or failure to perform preventive maintenance. And lastly, the error-free perfection. What are composite repairs? Comparing bonded repair versus bolted repair. Bolted repair is typically done on thick composite laminate structures. It involves drilling, drill types, countersinking, and knowing which fasteners to be used with composite laminates and fastener materials. When developing the design for a bolted repair, the repair engineer needs to account for, firstly, hard point effects, which is the load increase factor. Next, repair effectiveness to reduce stress concentration due to damage. Determining the repair materials which may be available, example titanium sheet, aluminum sheet, or what fasteners may be available, the type, the diameter, the grip length, and productability considerations, example like the bend radius for formed sheet stock, accessibility for drill motors, one-sided access, etc. And lastly, the capability of mechanics conducting the repairs. What are composite materials? Part 2 consists of thin skins bonded to honeycomb or foam core. They are typically called tapered or scarfed repairs. Tapering the repair area around the removed damaged piles in preparation for adhesively co-bonding a composite repair patch. It provides best load transfer and helps to ensure sufficient adhesive bond by maximizing bond surface area. Okay, so how is bonded repair conducted? Steps taken for typical bonded repair are: first, evaluate the damage. Determine extent of damage using visual and proper NDI inspection. Secondly, remove the damaged area. Take care not to enlarge the repair area. Next is taper sand a uniform taper around repair area. Taper sand accordingly per the type of repair. Next is dry and clean repair area, which ensure no moisture during curing of bonded repair. Cleanliness is very important to ensure proper adhesion. Number 5 is replace damaged core. Cut a replacement core to size and to be bonded to repaired area prior to patch bonding. Number 6 is to repair the repair plies and layout. Based on manual requirement and lay the plies per original orientation. Usually 1 to 2 extra plies are added for smoothing purposes. Number 7 is vacuuming back the repair. Apply pressure to repair during curing. 8 is cure the repair. Ensure proper cure cycle is applied. And last but not least, remove vacuum bag and inspect repair. To ensure structural integrity of repair, NDI may be required. How is bolted repair conducted? There is a perception that a bonded repair is highly susceptible to to process variability, and thus a bolted repairs are preferable. Bolted repairs exhibit process sensitivity as well as which needs to be accounted for. Meeting close tolerance hole requirements, using backup to avoid fiber breakout, shimming and feed-up stresses, which is the application of sealant, drilling through metal or composite stack-up. Metal chips can cause damage to composite holes, and drill wandering or hole misalignment if drill guides are not used, and deburring holes. When they occur, such failures in process are likely to occur throughout the repair and not at individual locations within the repair. What are the differences between the two types of repair? First is the bolted repair and the bonded repair. Category B repair for bolted repair requires inspection, while for bonded repair, it will be using Category A, which is permanent repair. Next, for bolted repairs, they have a faster processing time, while for bonded repair, they have a slower processing time. For bolted repair, they have a heavier repair, which means additional weight is added for the repair, while bonded repair is very lightweight. Next, bonded repair is not a sensitive material, while bonded repair is sensitive with time, temperature, and moisture. Next, it's bolted repair, drill holes done with care and caution, while bonded repair, no protruding parts or additional fastener holes. Last but not least, bolted repair, no risk of heat damage due to curing, while bonded repair, risk of heat damage on original structure and forming of porosity.
To produce aircraft is cost effective and is challenging now as it is. But now aircraft manufacturers are under increasing pressure to comply with strict environmental regulations to reduce carbon emissions. Which is compounded by the need to continually lower costs. But there are always ways that aerospace companies can produce aircraft cost effectively and be more environmentally friendly.
One method suppliers have employed to combat high costs and high carbon emissions is their use of composite materials in the development of aircraft parts. For example, due to their lightweight structure, composites are able to increase fuel efficiency and hence reduce an aircraft carbon footprint.
But there are also a series of other advantages to the use of composite materials in aerospace design and manufacturing that can help to reduce costs, but also boost the integrity of the structure of your composite part. Hence, we'll end our presentation now. Thank you so much.